Welcome to our first video on Chapter 1, Fixation. Now before we get started, I would like to go over kind of the overall structure of these videos, just in case there's some things you might want to skip, maybe something doesn't really appeal to your learning style. That's okay. I'm going to try to have these sections annotated so that you can kind of use the pieces that are most useful to you. So first off, we'll go over the goals of the chapter. So I'm going to kind of give you a heads up as to things you might want to focus on more, things that I've seen on the exam, and certain concepts that might help make the memorization work a little bit easier for you. Some of the terms that you go over are going to be just straight up memorization. There's not a lot of eloquent ways of learning some of the concepts, but others are going to be more processes. And so what we're going to try to do is use those processes, those very broad concepts, to sort of make it a little bit easier to understand those more concrete definitions. At the very end, I'm going to try to do something fun, something to look forward to. In this section, we're going to look at a fixative in action. So whenever you're ready, go ahead and get out your book. We're going to be covering the material as it's covered in the book, so that in case you don't want to look at my mug the entire time, you can look in your book and follow along. I am going to have some visual things. It might be a drawing, it might be a model, something to make these concepts a little bit easier to understand. So let's dive in. Let's start with goals. In this chapter, there's a lot of vocab. So what I would do is I would start with the broad concepts. So that's actually the first section on the first page with all the objectives. So it includes autolysis, fixation, artifacts, pigments, all of those things that you're going to use throughout the chapter. Get those down pat first. Then you want to move on to the reagents. Now these are different than the other chemicals. So some of the other fixatives are going to contain one or more reagents, but you don't really have to learn them separately, right? Because if you know if this has A reagent, B reagent, and A and B reagent do these things, and they're inside of the fixative itself, then you know that that fixative does the things of both A and B, typically. So that'll help take down the vocabulary just a little bit. Keep in mind when learning all the reagents is that the things like nuclear detail, the effects on the adipose tissue, carbohydrates, those are pretty minor. They're not things that you're going to have to keep in mind very often. The things that you really want to concentrate on are the comments and special uses. So if something's really good for electron microscopy, you should definitely take note of that. If something makes a PAS stain not work, you probably want to know that. And those are the things that typically come up on the exam. Because really, in a lab, that's what's really important. You're not going to want to put something in a fixative that you're going to need to stain for PAS if it doesn't allow for PAS. As always, if there's ever a concept that doesn't make as much sense after reading it or listening to me, there's going to be an activity on Histotutor. Feel free to go there. The instructions are now there. You just click on instructions, they'll pop up with a window, and it will tell you how to go about doing the activity. That will give you more kind of a hands-on approach to some of these things. In Fixation, we have an activity where you can either explore a reagent, so just pick on one of the reagents from the Explore menu, and that will give you all the details for that reagent. Underneath that, there's a Quiz Me function. You click Quiz Me, it will randomize one of the reagents. It'll give you all the properties without the name. You click whatever name you think it is from the menu, and it'll tell you if it's correct or not. So it's a good way to quiz yourself. Once again, when you're trying to learn these, while I have all the properties in the app, the really important ones are in the bottom. So that's the comments and the special uses, so keep that in mind. Before we start with how fixatives work, it might be important to think about why we use them in the first place. They take up a huge piece of the processing schedule. They're in fixatives, the tissue is in fixatives typically right after it comes out of surgery. So why so much time? Well, what fixatives do in a very broad sense, is they kind of stop the tissue in time, right? The whole point of this process, the whole histology process really, is to give the doctors a look at the tissue at the time of surgery. They want to be able to see into that person to see what's going on. And what fixation does is it stops the tissue. Now, it stops it in a lot of different ways. For one, it stops it physically from moving. Alright, so fixation keeps things in place. And it does that either by adding something on top, kind of like a band-aid to keep any two pieces of proteins from moving. Or it can attack the active sites by coagulation. And it'll take these pieces of protein that do all the work and just kind of cram them together so they can't work anymore. It's like bending a pair of pliers. You can't use them anymore. And along with those two things, there's also the fact that human bodies have bacteria inside them that like to eat things. And so after something leaves the body, you have to worry about putrefaction, which fixation also halts. Another factor is autolysis, which is different from putrefaction. And autolysis is just the body itself breaking down. Without any bacteria present, the body essentially starts to loosen. Autolysis means self-loosening. So essentially the tissue itself just starts to kind of break apart just from misuse and lack of maintenance. And when it does that, it loses its staining potential. So if you have something that's autolyzed, even if it's in something completely sterile, eventually it doesn't stain. If it doesn't stain, then the pathologists aren't able to look at it. Now, with all that being said, why don't we just pick one fixative that does all those things, right? Why don't we just do the thing that crams all the proteins in one spot, doesn't let them move, and stops the autolysis? Well, okay, yeah, you can do that, but there's one more factor to worry about, and that's solubility of a variety of substances. So we have proteins, we have fats, carbohydrates. All of these things have different reactions and different biochemical tendencies when put in these different fixatives. So for example, something like formalin will work really well. For instance, when we think about something like formalin fixes things slowly. And that's kind of a good thing, because if something fixes it slowly, then that gives us a lot of control as to where we stop that fixation. Because ultimately, if you fix something for too long, it can become brittle, and when it hits a microtome blade, then it shatters, in which case we don't get our section. On the other hand, we don't want something that takes too long, because these patients need help and they need it as soon as possible. As a result of this, what ends up happening is we tend to either mix our fixatives into one big fixative, or we use multiple fixatives on the processor, which is what we do at our lab. We use formalin, we use alcohol, and then we also use xylene and paraffin as part of our processing. But in terms of fixatives, formalin and alcohol are two main ones. And the reason that we use those two in conjunction with each other is they have two different actions. And you'll see these two different actions in fixation as we go over all the other reagents. Those two actions are additive and coagulant. As you can see, in formalin, it kind of makes a band-aid. It's an additive, right? So you have these two strands of protein here that would just love to just kind of squiggle around and move. And the more they move, the less true they are to how they were in the body. So what formalin does is it attaches itself to those proteins and stops them from moving. Now, formalin can't attach itself to every protein type or every amino acid. So we have to use ethanol or alcohol to kind of finish the job. And what ethanol does is instead of being a band-aid, it takes that active site, that pair of pliers, and just crumbles them. And by doing that, it stops the protein from changing its conformation and from acting. And that's what you want to do. You want to freeze these things in time. You want to stop them from acting. So between the two, formalin gets a lot of the things, ethanol finishes the job, and then we go on with the rest of the processing. Now, with either of these, you have the possibility of hardening. So with formalin, the problem is that if you add too many band-aids onto the proteins, eventually when you put it on the microtome, you're just hitting the band-aids. You're hitting crystallized formalin, essentially, and it doesn't cut well. With ethanol, if you put it in there for too long, these proteins keep balling up until they condense, till they're very, very dense, to the point where they become hard. When you hit something that's very, very dense, like a calcification, it doesn't cut well. And the same thing can happen with proteins if you leave them in ethanol for too long. So as I've mentioned earlier, when we're thinking about fixation and how long something should work and how strongly it acts on the proteins, we not only have to think about what the doctors are looking at, but we have to think about microtomy. So if you think about, to kind of take it away from being human, think about hamburger, right? If you put hamburger and embedded it, put it in a paraffin block, it wouldn't cut well at all, right? It would just be mushy and it'd be a mess. But if you cooked it just like a good steak, you put it in some paraffin, put that on a chuck, it would probably cut. It would probably cut fairly well. And then if you burn the steak, it would just be crumbly and it would fall apart. Okay, so if you want to avoid some of the lingo, just think of it like cooking a steak. Okay, well done's where you want to be. Burnt doesn't cut. Raw doesn't cut. It's got to be somewhere in the middle. Now you might be thinking, well, we've put things in formalin for a long time, right? Things might be sitting up in the OR for a while, and then they'll come down and engrossing their formalin for a while, and that's not always completely controlled, and they're putting formalin in the processor. That's a lot of time of formalin. So why doesn't the tissue get super hard all the time? Well, for one, remember that formalin works slowly. So you do have a lot of time. You have a lot of control over it before it becomes too hard. And there's a big window there where it's optimally fixed. Also, when it's in the processor, it's being heated. And heat is another way to process tissue, somewhat. So what heat does is it acts kind of as a coagulant. It does coagulate some proteins, but it also makes the chemical reactions act faster. So if you want to make any kind of chemical reaction act faster, you want to either add heat, which increases the kinetic energy, so essentially moves the molecules around faster, makes them interact more, or you want to add aggregation, which essentially is adding heat but very, very slow, or very low amount. And so that is how tissue, if it's left in the formalin for too long in a processor, becomes hard, because the formalin is acting much, much faster than it is on the outside because of the heat. While we're talking about heat, let's just talk about the factors that can affect fixation along with heat. You also have the size of the tissue. Sometimes you might find a piece of tissue in a cassette that just barely fits in there. You can tell that it was kind of put in and they smushed it shut. You can see the grid lines on it. Chances are that tissue is going to be too thick. Those cassettes are made to be at an optimal thickness, which allows for the tissue to have lots of life while being cut, while also being optimally fixed. So our processing schedule is made for nothing to be any bigger than what can comfortably fit into one of those cassettes. So if it's smushed in there, it's going to be too big. The reason that that's such a big factor is that our fixatives have to attack that tissue, and they attack it from the outside. So if it's too thick, you might get fixation on all the outside edges, but in the middle it's going to be soft. So that when you cut into it, even if the outside is firm, that inside is going to give. And so as the blade is trying to push into it, it's going to push into that soft center, and the firm stuff is actually going to push in a little bit because of that give. And then you're going to get bad sections. Another thing is volume ratios. And this comes into play when you're talking about how many cassettes, essentially. So you can only have so many cassettes in a processor at any one time, because at some point you can have too many cassettes in too little of an amount of reagent. So you have to have a certain amount of excess reagent, excess volume of reagent, compared to the number of cassettes. So if you were only fixing 3 cassettes, you could probably put them in a very, very small container and fix them adequately. But because we do a few hundred cassettes, we use the really big processor. Another factor is time. As we know, when we set a processing schedule for tissue, we have very specific times when it can go in and when it comes out. And that's because depending on the fixative that you're using, the amount of time it takes to fix adequately changes. And so you don't want to put it in take it out too soon, because then it won't be fixed. And if you let it in there for too long, then it's going to be hardened. So time is a factor, and all these things kind of work together. As it turns out, time is incredibly important when we're talking about HER2 testing. HER2 testing is something that we do in IHCs. It has to do with breast cancer. We're not going to get into the specifics of that right now. But what we do want to make sure of is that any breast tissue that is in 10% initial buffered formalin is in there between 6 and 48 hours. No more, no less. Anytime outside of that is either going to be not fixed enough, to a point where it probably won't cut. But if it's fixed for too long, it'll probably cut just fine, but the HER2 testing will not work. It will lose what's called antigenicity, and it will no longer be able to be tested adequately for HER2, as it may show some false negatives. While we're talking about time, we should talk about something that's highly related, and that's penetration. And penetration is essentially how long it takes for a certain fixative to make its way through the tissue. And so the rate of penetration is going to affect how long you want to actually keep that tissue in the fixative. Now that we know a little bit more about the factors that are part of fixation, let's talk about specifically what we're trying to fix. And that includes DNA, RNA, proteins, lipids, and carbohydrates. So when we think about DNA and RNA, that mostly resides in the nucleus. So when we're saying the nuclear staining is good, bad, we're actually saying that the DNA and RNA staining is good or bad. And that's pretty important when you're trying to see if cells are dividing or not, or if they're about to divide, and seeing what the state of the DNA and RNA are inside a cell, which is a big part of diagnosing things like cancer. And that's why nuclear staining is so important. Luckily, with the fixatives that we use, while the DNA and RNA tend to be preserved, they're not directly interacted with. And this is important because while they are fixed and while they're visible, they are still able to be sent out for things like DNA and RNA analysis. We can run things like kappa lambda probes back in IHCs. We can do all of these things because while they are intact, they are not actively being altered. Now when it comes to proteins, proteins provide a lot of the structure. So when we're talking about preserving proteins, we're talking about preserving the overall structure of the tissue itself for the most part. So you know that your proteins are fixed well when things are not mushy and they cut well. That's a big part of it. Now, on the other end of the structural part is the lipids. So if we have, for example, in a piece of breast tissue, we want to make sure that the lipids are fixed properly because there's a lot more fat in there compared to the proteins, and if the lipids are not fixed correctly, it won't cut well. In terms of carbohydrates, essentially you just don't want to lose too many of them. You're going to lose a lot of them in most fixatives, except for some of the aldehydes, in which case PAS testing is no longer usable. So the pathologists know that some of the carbohydrates are going to be lost almost no matter what we use. And the things that do preserve them don't allow for carbohydrate testing, so it's kind of a whole thing. But the important thing to remember is that we're trying to preserve the nucleus, which is the RNA, DNA, proteins, lipids, and the carbohydrate. Just as a note, within the book, you're going to see things like additive, non-additive, coagulant, non-coagulant. I tend to refer to them as additive or coagulant. Those tend to be the two classes that you're really looking at. But just know that if something is, for example, non-additive, it's probably a coagulant. And if it's a non-coagulant, it's probably an additive. That's just something to keep in mind. The book tends to flip-flop around on that, and different editions of the book have changed. So just keep in mind, things are typically either additive or coagulant. It turns out that acetic acid is the one exception to the rule as far as being additive or coagulant. It's neither. It doesn't really affect proteins at all. It just affects the DNA and the RNA. So this is a non-coagulant, non-additive, but we still use it because it preserves the DNA and RNA very well. On to the reagents themselves. This is a long chapter for this. I realize that there's a lot of reagents to go over, but I believe in you. You've got the stamina. We can get through this. So let's start with acetic acid. While it's doing that, acetic acid in particular tends to space them out a little bit, which allows a little bit of things in between there, which causes them to swell. Okay, so the proteins themselves actually swell up a little bit. And that's a problem if you're trying to keep things preserved, such as red blood cells. So red blood cells tend to lyse in things that have acetic acid. To make up for that drawback, acetic acid is really good at preserving nuclear details. So our RNA and DNA is very, very well preserved with acetic acid. Next we have formalin, or formaldehyde, or both. So essentially you're going to hear both terms. Formaldehyde is essentially the chemical itself. Formalin is a way of referring to a certain concentration of formaldehyde, which is really confusing, and it'll always be confusing. It's strange. So let's just get down to that first off before we get into the characteristics of formalin or formaldehyde. Interchangeable. So 37 to 40% formaldehyde. So let's say a 1 liter bottle of that is in fact 100% formalin. So formalin is just 37 to 40% formaldehyde. Okay, so 40 mils of formaldehyde and 60 mils of water makes 100% formalin. So a lot of times you're going to hear things like 10% neutral buffered formalin. What's in that? Well, you would take that 37 to 40% formaldehyde, right? You take that solution and take one of that to 9 parts water, right? So 10 mils of formaldehyde, sorry. So 10 mils of formaldehyde to 90 mils of distilled water makes 10% formalin. It's weird, it's hard to get used to, but I promise that there'll be exactly one question about this on the exam. Now on the other end of that, so we have something that is formalin, which is technically a dilution of formaldehyde. On the other end, we have paraformaldehyde, which is what happens to formalin or formaldehyde when it sits around too long and doesn't have any methanol in it. And what it does is it makes this white precipitate. Okay, precipitate is just a chemical that becomes a solid out of a liquid, right? It's basically concentrated formaldehyde, sort of. It's a polymer of it. So if you take that white powder, and you add it to some water, it makes 10% formalin from about 4% paraformaldehyde. So instead of diluting formaldehyde, you can actually take a solid paraformaldehyde to make the same amount of formalin. So it's kind of, you can have very dilute formaldehyde, formalin, and then paraformaldehyde. There's kind of different concentrations, essentially, of the same thing. Now that we know the basic permutations of formaldehyde, let's talk about what does it actually do. So formaldehyde, as we know from previous parts of the video, is an additive. Okay, it makes those little band-aids on the proteins that holds them together. And so by adding itself to the tissue, it's holding it in place. And it's not a coagulant. So if there are any active sites that are not cross-linked, which is our word for the little band-aid, if they're not cross-linked like that, then they're still active. So that's why we have to usually follow up with something else or add something to the formalin to complete the fixation process. With that in mind, why use formalin if it doesn't do the whole job? Well, formalin, for one, as we know, takes a while. So there's a lot of control there. You can put something in formaldehyde and up in the OR, bring it down, transport it, accession it, do all the things, and it's not going to become hard before it's ready to cut. Also, formalin leads to the least amount of shrinkage of any of the other reagents, and that's really important because when you're trying to look at, let's say, a tumor or anything that's growth related, you need to know the size of it relative to everything else. And if something is shrinking things, you don't know if some things are shrinking more than others. But if formalin or formaldehyde leads to less shrinkage overall, that's a great thing as far as making an accurate diagnosis. Along with the fact that it's an additive and not a coagulant, meaning that not all the proteins are going to be preserved, it has an odd effect on lipids in that formalin will fix them, but it doesn't necessarily make them insoluble, meaning that some of them can still be taken out later on in processing when it's in the alcohol or in the xylene. Some of the fat's going to come out if it's in formalin for too long. And part of that could play a part in the HER2 regulation, but it's also just in general. You don't want to lose fat or adipose tissue if you don't have to. One of the things that you will find in formalin and also some other reagents is the fact that they make pigments. And a lot of times pigment creation has to do with the tonicity or the osmolality of the reagent. And so what we do with formalin is we try to buffer it, typically. Typically we will use what's called a neutral buffered formalin, and what the buffering is doing there, it's keeping the pH and the tonicity, or the amount of water to solute and the ionization that's going on in that reagent at a level where pigments aren't being formed. So when something has too much of something relative to the outside, so too much concentrate relative to the things around it, it can create pigments, which is essentially just a concentration of formalin that shows up on the tissue, which is a problem, right? So when the doctor's reading something and they see a piece of formalin just kind of hanging out right over something, maybe they're trying to look at a tumor, maybe they're trying to look at some cells and try to figure out what's going on, there's just a big old piece of formalin in front of it and they can't read it. So that's why we typically buffer formalin. Now formalin over the years has had many things added to it to try to buffer it in some way. Some folks have added calcium, some people have added ammonium bromide. We've done things by modifying it differently. Most labs, including ours, use neutral buffered formalin, meaning that there's an actual buffer added to it that keeps the pH and the tonicity where it needs to be to prevent that formalin pigment from showing up. Talked about formalin and alcohol being used in processors a lot, including the one in our lab. You might wonder, why not just put them together and let them do their thing all at once? And that way you could just use 3 alcoholic formalin stations, right? Well, yeah, that's what some places do. So you can do that. You mix it up in lab. But the thing is, if it gets to be outside of that concentration, then precipitates start to form. So it has to be really well maintained, and alcohol tends to evaporate, and so when you're adding heat to things, things can change rapidly. And so you don't want to botch an entire run because some of the alcohol may have evaporated. So it's a little more dangerous in that respect. If you have a really well maintained lab and very, very strict guidelines for your reagents, it can be a great thing because that will essentially cut your processing time in half. Another thing to note about alcoholic formalin is that it's something that tissue can be placed in indefinitely. So it turns out that all the factors that go into formalin and all the factors that go into alcohol kind of work with each other. So the shrinkage that comes with alcohol tends to be lessened because of the formalin, and because you have both an additive and a coagulant in the same spot, you're getting complete protein preservation. So that's what makes it essentially a great thing to store things in for a long period of time. Before we get away from formalin and formaldehyde, one thing to note, it's almost definitely going to be on the exam, is the PEL and STEL of formalin / formaldehyde. So what the STEL is the short-term exposure limit, meaning that you can have an exposure of 2 ppm, or parts per million, per 15 minutes, as long as it's under the PEL, which is an 8-hour limit. The PEL is 0.75 parts per million over an 8-hour period. So if you are exposed to more than 0.75 ppm over 8 hours, or over 2 ppm in 15 minutes, you've gone over the limit. OSHA says this is not a safe place to be. Stuff is glutaraldehyde. Glutaraldehyde is a lot like formaldehyde, except it has an extra aldehyde group on it. Now that extra group doesn't really interact with the tissue so much. So the first one does all the cross-linking, same way that formalin does, so it's an additive. But the other aldehyde group is just kind of hanging out there, ready to react with anything, including Schiff's reagent, which is in a PAS stain. So if you were to run a PAS stain for aldehydes, then the entire tissue would turn pink, in this case, because of if it was fixed in glutaraldehyde. So that means that if you're going to do something that needs a PAS test, you cannot use glutaraldehyde. Definitely take note of that. That's mostly what's known for. The other thing is its special use, and that is in electron microscopy. Out of all the aldehydes, it preserves things best for electron microscopy. And what's important in electron microscopy is ultrastructures. So things like mitochondria, vesicles, Golgi apparatus, all those things are preserved really well with glutaraldehyde. Next is another reagent that acts a lot like formaldehyde, and that's called glyoxal. Glyoxal is used because of its ability to cross-link, much like formaldehyde. It adds itself right to the proteins and keeps them in place. In fact, it cross-links so well that it's used in industry for things like permanent presses. The reason that you don't see that a lot in laboratories is that reaction, where it does the cross-linking, only happens in a narrow range of pH. So keeping something in a narrow range of pH can be kind of hard. Buffers can be expensive, and that's essentially what you would need to preserve that range of pH. So either there's expensive buffers, or even just the fact that in a laboratory mistakes happen, and pH can change just because something was left out, something like that. All of a sudden your glyoxal just doesn't work at all. And it starts to either precipitate or break down. So glyoxal is great when it's used properly. And it's been often tried as a formalin substitute because it is still toxic, but it's less toxic. Because we know formaldehyde's a carcinogen. I mean, that's been discussed widely. Glyoxal is harmful, but it's not necessarily as bad as formalin. Our next reagent is one that is not really used generally anymore, but it's still studied for historical purposes, and that's mercuric chloride, which is exactly what it sounds like. It's mercury, all right, with a chloride group. And so why use mercury? Well, it turns out that it preserves fairly well, but the big pull is that it makes the tissue really, really receptive to dyes. So the ending stain is just magnificent. Obviously the problem being that there's mercury in it. So not only is mercury very toxic to people, but it is also a corrosive agent. So mercuric chloride will break down any metal that touches it, and so it becomes a real hassle if you're trying to clean it, because you don't want to get it on you, you can't get it on any metal, and you have to clean up after it very quickly, and you have to catalog its use, they say, from cradle to grave, meaning that from the time it enters your lab to the time it exits, it has to be logged. And it's just not worth the extra staining potential. And the second problem with mercury is the fact that it makes a pigment. Now, unlike pigments that can be found in formalin, the pigment in mercuric chloride is there no matter what. It comes with the fixative, it's already in the tissue, though it can be removed with the use of iodine, which mobilizes it, and then sodium thiosulfate, which we'll see later in special stains is often used to remove excess metals from things. So iodine, sodium thiosulfate will get rid of a mercury pigment. But just remember that the pigment is always going to be there, and it's always going to have to be removed before that tissue can be seen by a pathologist. Our next reagent is picric acid. And picric acid is another odd one. So it doesn't really preserve anything incredibly well. It acts a lot like mercury did in that it makes things easier to stain. So things that are acid dyes work extremely well with picric acid. So what you kind of have to do is put it in there, make it, usually want to do that after fixation, after regular fixation. And you put it in there and then wash it out. Wash out all the excess because it just wrecks everything else. DNA, RNA can become soluble, and so they'll kind of wash out. The other thing with picric acid is that if it gets dry, it can become a contact explosive. So we don't like that. With all that being said, picric acid does have some uses. It can be used to remove calcifications. It can also be used to prep tissue for acid dyes. So, for instance, in Masson trichrome, you might use picric acid as part of buvins to prep the tissue for the acid dye. Next up is potassium dichromate, which is essentially has chromium in it. So it's kind of in that same class as mercury, where it has a very dangerous metal that's to be tracked from cradle to grave. So that's not great. But the one thing that potassium dichromate does well is preserve mitochondria. So if that is specifically what you're going for, you can use that. Another drawback is the fact that it produces a pigment. Anytime you go from potassium dichromate to alcohol, it produces a pigment, and in this case, which is different than mercuric chloride, the pigment cannot be removed, according to most authors. So once it's in there, it's in the way, it's going to get in the way of your diagnosis anyway, so most folks just avoid potassium dichromate. Next reagent is zinc. Now, zinc has been used as somewhat of a substitute for mercury, and over the years people have tried to just put it in other things you put mercury in, and it kind of gives it that ability to get the dyes to be more vibrant. So as time has gone on, people have thought, well, we have formalin, which is good, alcohol, which is good, alcoholic formalin is very good, but what if we could have that mercury effect in alcoholic formalin? What if we can make a really great fixative out of all of those things? But we don't want to use mercury, we have zinc. And so that's essentially what has happened fairly recently, is that folks have taken alcoholic formalin, so as you remember, it does the cross-linking, it does the coagulating, now you're adding some zinc to it to get that better dye, and when everything works well, big caveat, when everything is working well and things are made correctly, it just makes some fantastic stains. Next we're going to get into our compound fixatives. Essentially what these are the reagents that we just went over, added together into a new fixative that tends to take all the properties of the reagents and put them in one spot. Now sometimes the reagents might lose a characteristic or two, or they might gain a new one because of the interaction between those, but for the most part, if you know what's in a compound fixative, you can go by what those properties are and just kind of add them together. So let's say if something like acetic acid does swelling, picric acid tends to shrink things when it's with something else. So if you have swelling and shrinking, then you get something in the middle. So you might add things in a compound fixative to kind of counteract the bad things while keeping the good thing. Our first compound fixative is B5. So in a traditional B5, you have two components. You have your mercuric chloride, and you have sodium acetate, which turns into acetic acid, essentially. So if you remember back, mercuric chloride has that really nice staining while also being really, really toxic. And then you have the acetic acid, which tends to swell the tissue and lyse red blood cells. So what could this be used for? Well, B5 tends to be used in things that have a ton of red blood cells in them that kind of get in the way. So in this case, the red blood cells act kind of in the same way that pigment does, and that they get in the way of what you're trying to see. So a piece of spleen, for example, might just have red blood cells everywhere, but you're not looking for those. You're trying to see the tissue around them. So you put them in B5, it lyses the red blood cells and kind of washes them away so that you can see all the underlying tissue. Our next compound fixative is called Buin. And in a Buin solution, you have picric acid, you have formaldehyde, and you have acetic acid. So let's think back. When you're thinking about picric acid, you think of some shrinkage, but also it might get rid of anything that's hard, which tends to like soften all the tissue around it. Then you have formaldehyde, which does everything it normally does. It's additive, it cross-links proteins. And you have acetic acid, which tends to swell things and lyse red blood cells. So where would you use this? Well, you can use it in bloody tissue, much like B5, because you would get rid of all of the red blood cells that you don't want. But typically you use it as a mordant from a Mason trichrome stain, which we haven't gone over yet. It's okay, don't panic. Just know that when you think Buins, think Mason trichrome. It's the first thing you do, is you put the tissue in Buins and then you go on with the rest of the stain. So after you do that, once something's in Buins, no matter what you're doing with it afterwards, you need to wash it, because it's going to turn yellow. And that yellow is not going to be great for further staining, if you have a yellow tint to everything. Next compound fixative is called Gendra, or Gendra? I don't know, I've never heard it out loud. We'll just call it Gendra solution. It has alcohol and picric acid, which is in the form of alcoholic picric. We have formaldehyde, and we have glacial acetic acid. So between all of those, we have some swelling, some shrinking, lots of preserving, right? Between the formalin and the alcohol, they preserve basically all the proteins. And the glacial acetic acid does some swelling, which kind of moves things around a little bit. All in all, Gendra solution is used for carbohydrates. It's really its one use. It's the one thing it does well. For some reason, all these things working together just keeps carbohydrates really well preserved. Our next compound fixative is Holland solution. Now, Holland solution has a lot of things in it. The things you want to keep in mind are red blood cells and GI specimens. Those are the two things that Holland is really good at preserving. It has copper acetate, picric acid, acetic acid, and formalin. So the picric acid and the acetic acid kind of cancel each other out in terms of the swelling, which kind of just makes them perfect for red blood cells. Now the rest of the effects, as far as for GI biopsies, that's not really that well understood as to why Holland works so well. Our next compound fixative is essentially just formaldehyde and glutaraldehyde, which is formaldehyde, glutaraldehyde. It's 4CF-1G. I've never heard anybody refer to the actual reference number. Just remember formaldehyde and glutaraldehyde, when put into a compound fixative, can get kind of the best of both worlds, but not really. It's essentially a formalin that can do better electron microscopy, but also cannot be used in a PASF or a PAS, or can also not be used in a shift reaction. So if you have things that are routinely used for formalin fixation, but you do a good bit of electron microscopy too, and you don't have to look at carbohydrates very often, then formaldehyde, glutaraldehyde might be useful. Our next two compound fixatives tend to be talked about together because they have the same stock solution, and that's Zenker and Heli. So the stock solution for these is just mercuric chloride, potassium dichromate, and some water. So those two really toxic reagents we talked about are in the same stock. So that's a really toxic stock. The difference between the two, between Zenker and Heli's, is that Zenker has acetic acid added to that stock, and Heli's has formaldehyde. So this is really, really toxic stuff. So why were they made? Well, these were pretty early solutions. Obviously, they have all the really toxic stuff in them. So Zenker, because it has the acetic acid, will lyse red blood cells. So if you have a piece of spleen, it might look a little bit better because you get rid of all those excess red blood cells. Whereas in Heli, you know, the formaldehyde, which will tend to preserve those red blood cells a little bit better. Nuclear detail is better in Zenker. So Zenker can be used for decalcification. So let's just go back over it. Zenker has the acetic acid. It's better for nuclear staining. It can do some decal. Heli has formaldehyde and it preserves red blood cells. Our next compound fixative is called orth solution. And the orth solution contains potassium dichromate, sodium sulfate, and formaldehyde. And don't think too much about the individual reagents, because orth solution typically is only used for one thing, and that is to find chromaffin granules. Where we tend to find chromaffin granules is in the medulla of the adrenal gland. And so what will happen is, at grossing, if the patient is suspected to have a pheochromocytoma, the actual PA will stain the medulla with orth solution. And if it turns kind of a yellowish orange, then it's probably positive for that. Our next compound fixative is called Zamboni solution. Zamboni uses the paraformaldehyde, which remember is a polymerization of formaldehyde. So it ends up being more of a concentrated form in a way. So you add that, you add some picric acid to it, and some sodium phosphate, which essentially makes a buffer. And you add all those things together, and it becomes a general purpose fixative. It's not widely used, probably because of the picric acid, because picric acid, as we know, explodes if it gets too dry. So that's essentially what that is. It's a general purpose fixative. It's not really notable, but you really should know that the reagents that are in it. So as we mentioned before when we talked about zinc, zinc can be used in compound fixatives. So you can have zinc formalin, you can have zinc alcoholic formalin, and all of these things just take all of the good things about those other reagents and put them into one big fixative. And anything that has zinc in it is going to have some pretty good nuclear detail, but something maybe even more important is it tends to retain antigenicity, which we'll get into when we talk about IHCs. But essentially it makes it so that IHCs are better. They're easier to get. So it makes the things that IHCs react with more readily accessible, and it actually undoes some of the damage that formaldehyde does towards the things that we look for in IHCs. So just remember, zinc is just a really good additive to things. It makes a really great compound fixative. Zinc alcoholic formalin, which works amazingly as long as you get everything right. Our next class of fixative is going to be non-aqueous. So everything up until now has had some amount of distilled water in it. And all of our non-aqueous fixatives tend to be non-additive, so they don't actually make that band-aid onto the proteins. They tend to be coagulants. So when they interact with proteins, they tend to crumble them up. They take that pair of pliers that the protein's using to do work and crumbles them, so that they're inactive. Really only 3 reagents in this class, and those are acetone and methanol and ethanol. You can talk about things like isopropanol and things like that, but essentially the alcohols and acetones tend to act similarly in terms of as fixatives. And we're also going to have some compound fixatives, which are going to add these in different amounts, plus some other aqueous solutions. First compound solution in this class is called a Carnoy solution. Carnoy solution is just absolute alcohol, so 100% ethyl alcohol, chloroform and acetic acid. And what the carnoy is used for mostly is cytology. So if you have a cytology specimen, let's say it's sputum, right? It might have some blood in it. The carnoy solution is going to destroy all the red blood cells, because we know when you're looking at a cytology slide, you're looking at individual cells. So you might not have a lot to look at to begin with, and you don't want a bunch of red blood cells getting in the way of that. The next compound fixative in this class is Clark fluid. Now, Clark fluid was used a long time ago, and is continued to be used in some places in place of other fixatives for routine paraffin embedding. It's just alcohol and acetic acid. Now, we know that both of those things have their problems, but so alcohol can have some shrinkage, whereas acetic acid tends to swell. Those two things come together and they kind of balance each other out. So what you're left with is a coagulant. And so it's fast acting. The only thing is you lose the control that comes with formalin, because formalin takes a little bit longer and has a much bigger window of optimal fixation compared to something like Clark fluid. So we have a few transport mediums. Because sometimes when you take something out of a patient, your facility might not have what it needs to perform the testing. So you need something that's just going to keep it in the exact state that it's in without getting it ready for embedding. So you want all the antigens to be where they're supposed to be, you want all the proteins to be in the same spot, but you don't want them to break down or be fixed to the point where when you send it to the next place that they can't do what they need to do. So that's where you might use a transport solution. Our first one is called MECO, transport medium. It has citric acid, ammonium sulfate, N-ethylamylamide, and magnesium sulfate. Essentially, MECO transport medium is used exactly what it sounds like. You put the tissue in it, throw it in a cooler, and send it off. The medium is good for about 6 months, and the whole point is so that the tissue stays exactly as it was when you put it in the solution. Another transport solution is PBS sucrose. PBS sucrose is used specifically to keep immunofluorescent specimens in that present state. So if you're sending something out for immunofluorescent studies, you put it in PBS, put it in a cooler, send it out. All it has is your PBS solution, which is potassium phosphate, sodium phosphate, and sodium chloride salt. You put all those together and you add some sucrose to it, and it keeps things active on when you do the immunofluorescent studies. So let's say you've done your fixation and you're wondering, did it work the way you thought it would? Well, there's certain ways that we can look at tissue to check that. So every morning in our lab, we run a test slide to see if our staining is working well, right? And we're typically looking for the nuclear detail, eosin staining, and that's mostly it. You add a third characteristic to that, and you're looking for fixation. So you also want to look at shrinkage. You want to see, is everything in the correct proportions on that slide? If you have all three of those things, the nuclear staining, cytoplasmic staining, and the aspect ratio of all the different pieces, then you have good fixation. Now sometimes you're going to look at that slide and you're going to know things did not go well. In some cases it might be autolysis. It might be that you didn't get the tissue to a fixative quickly enough, or maybe your fixative was too dilute. In that case, the body itself just kind of did the autolysis, meaning self-loosening, where all the proteins just kind of start moving apart from each other and things aren't where they're supposed to be. Autolysis can't be reversed. Unfortunately, once it's done, it's done. You kind of have to make do. Sometimes you have incomplete fixation. In some cases, the tissue might be like mushy, or you can kind of tell at embedding, sometimes the microtomy thinks that something's wrong, in which case you can put it back into a fixative by reversing the process. So you'll throw the block itself in xylene, get rid of all of the paraffin that's in there, then you put in alcohol to get rid of some of the xylene, and then you'll flush that out with your fixative, and then you put it back through the processor. So you basically do the process in reverse, then put it back in the processor to kind of complete fixation. Though sometimes you don't even catch it then. It's already on a slide, in which case you're going to see some incomplete staining on the nucleus. You're going to see cytoplasmic staining that just doesn't look right. It might be pale, or it might not have all of the shades that are supposed to be there. Or you might see that some cells are a lot bigger than they should be, or a lot smaller than they should be, in which case you might have had a bad choice of fixative, or perhaps was in there too long or not long enough. That about wraps it up for fixation. This was the first chapter. Congratulations, you got through it. I would say my advice to you would be to go to the beginning of the chapter and look at the objectives, see if you can go through those. If those make sense to you, you don't necessarily have to memorize every minute detail, but if you understand what's going on and you remember the key vocabulary that we went over, then you're probably good to go. I also advise you to do some hands-on stuff. Go to the Histotutor site, quiz yourself, see how you're doing. If you can look at all the characteristics of a fixative and know what it is, then you're probably okay for this chapter. Now, we did a little bit of an experiment when we started recording today. So, kind of tried to reenact the egg thing in the book. So we put a raw egg in some alcohol, which I'm pretty sure is isopropyl. Yeah, 91% isopropyl alcohol. And as you can see, it coagulated. It sure did something there, didn't it? The whites are pretty well coagulated. This happened about 3 hours ago. So this is 3 hours of fixation. We essentially chemically cooked the egg. And that was the fun part. It was fixation. It was really hard to find something fun to do with it. But we chemically cooked an egg. So if you want to, you can try reenacting this at home. Try some different things. Let me know how it goes.